we were talking about the temperature correction factor tables in National Electric Code, and we learned that one of the most important things is to read the actual heading, because in the heading there's a qualifier to this chart that's at a certain temperature range, and as we'll see in just a bit, this same chart will appear multiple times in code. And if you do all of your calculations based off the chart that's at 86 degrees Fahrenheit, whenever you go into other tables that have to do with other kinds of ampacity derating, you might get different temperature ratings. You need to make sure you look up in that title and make sure your temperature is matching. It's, to me, I think it's kind of confusing that they have these kinds of different charts, because you'll get to the same point whether or not you use all the 86 degree Fahrenheit temperature charts or you use all the 104 degree Fahrenheit temperature charts. The end result, the end sizing calculation will be exactly the same. Anyway, we'll get into that in a minute. How do you read this chart? We basically, the hotter in temperature you go, you need to start having higher temperature rated conductors, to the point where lower temperature rated conductors, when they begin to exceed their temperature rating, code is saying, that 60 degrees Celsius cable cannot go in a 80 degrees Celsius, environment. Otherwise it'll start burning up. Remember, those cables already generate their own heat from the electricity inside them. And so, by the time you get into extreme rooftop temperatures where your cables are 1 inch from the rooftop, you have to be using 90C rated cable just to have something that can be safe up on the rooftop. But actually, this isn't so bad, because it's not just ampacity sizing in cables. It's the friction of the electrons as they're flowing through on the cable jacket itself results in losses called voltage drop. So you often upsize solar cables anyways because of voltage drop. So you could easily be up on the roof using 30, 40 amp cable for an 8 amp circuit, and it'd be perfectly fine in terms of the conductor being able to withstand that extreme heat. Because only a third of the tube that's inside of it is full of electrons, and the other 2/3 are helping those electrons travel through and dissipate that temperature. And what we also see kind of on the other end of the spectrum is, if we're using high temperature rated cable in a cold environment, it's giving us a the original calculation, the 100%, is done at this like 86 degree Fahrenheit. And so if we're actually at a lower operating temperature than 86 degrees Fahrenheit, we get to add ampacity capacity into the cable rather than subtract it. So here we have a different table, and this is much further along in this same kind of section 310 of code. We see this ampacity table at 310.15, then a couple pages later you see at 310.60, the same ambient temperature correction factor chart, except it's done at 104 degrees rather than 86 degrees. Like, I have deja vu or something. I thought I just saw that. Well, it's the same chart. The only thing that's different is all of these fudge factors have been calculated based off, assuming that the starting point temperature is 104 instead of 86. And that's the only difference. So it's kind of weird. The most important thing is to be consistent and make sure your temperature title matches. So I just think it's most convenient to just start with the chart that's up first and use the lower temperatures and higher temperature derate factors. And so what we see here is, instead of calculating this table using 86 degrees as a reference point. We've calculated the same table using 104 degrees as a reference point. And since our starting reference point was higher, when we get into real ambient operating temperatures, we don't have to derate as much as if we're using the lower temperature. And so because these fudge factors were calculated based off a higher reference point, you don't have to discount as much because you've already built an additional 20 degrees of Fahrenheit into the fudge factors. So it can be kind of confusing if you're just looking at these charts and say, when do I use this or when do I use that? You just have to read the titles. Stuck in these title addendums are additional details. Like you'll get ampacity charts for conductors inside of conduit versus in free air. And that, because a conductor in free air has much better temperature dissipation than inside of conduit, will have a different ampacity rating than inside of conduit. So you have to read the title, the chart title headings, and make sure that the modifier in the title heading kind of makes sense for your case. So in addition to the difference between a conductor being inside of conduit versus in free air, that would be one difference in operating heat. Another would be if you have multiple cables carrying heat bundled together, whether they just be thrown in the ground or inside of a conduit, perhaps even outside of a conduit, depending their spacings. But this says, look, when you have more than 3 cables bundled together, you have to further derate its ampacity. Actually, not a huge deal. I don't, the reason why some of these tables are incomplete is I can't give you a complete copy of National Electric Code for you just to print out and have as a handout, unfortunately. So there's middle data, inside of here, but what we're trying to do is illustrate the point. The more conductors you have bundled together, the greater the derate. So we see starting at 4, you have to derate by 20%. And then once you get into a couple dozen conductors, you're derating by over 50%, 55 to 75%, or 65%. So actually, if you have a whole bunch of solar circuits that are oversized because of voltage drop, and you're not, and then you start bundling them together, that starts to get into, okay, well, am I bundling it to go across a walkway, or am I, is it going to be a short section? Is it a bundle that might be 1 or 2 feet, or is it a bundle that is 10 feet long or more? You have to start applying these derating considerations. Actually, 3 feet or so. So then we have so ambient temperature correction factors. I guess we've maybe this is a redundant slide. We've seen this already. Okay, so now we're getting into, so this is still like section 310. Remember, this is wiring, and so if you're flipping through codebook, if you don't need to memorize the actual individual numbers, but if you know that section 300 is the wiring cabling section, and this is pretty basic stuff, it's going to come towards the front of the section. Then you start thumbing through your charts and then reading these titles. So this one is based on 86 degrees, and then separately there's another chart that's based on 104 degrees, and then says the ampacities in this chart are for no more than 3 current carrying conductors, because otherwise you'd have to go and apply additional derating, between 20 and up to 55, 60%, like we just said. And then it says this is in a raceway, and then there's a different chart for free air, and then a different chart with wind that has different ampacities listed. And then different cable jackets, we've already pointed out they have different temperature ratings, and so a cable jacket with a higher temperature rating can hold more amperage and have less temperature derating due to heat than a cable that's not designed for a harsh environment. And that really comes into play when you start using indoor cable versus outdoor cable. They can make indoor cable a little bit cheaper, and that cheapness means you can't do as much with it. So now we're looking at some just basic conductor ampacities, and we can see that there's a wide range of cables, but a number 8 cable that's rated for 40 amps. If you're using a kind of a cheap indoor cable, there might be another number 8 cable that is rated for 55 amps. So what do all these cable numbers mean? We're engineers, and so we like to label things, and we like things to have a very technical meaning. We're going to, just in a couple of slides, we're going to get to a section in code that explains. Here we go. We talked about this yesterday about even when you're throwing cables into a trench, you have to space them out in order to avoid them being considered to be bundled together for heat dissipation. Going the wrong way. There we go. So now we get to a section that defines what all of those table wiring acronyms mean. MI stands for mineral insulated. These are conductors. Sorry, not cables. We have a plastic skinned cable. We have a moisture resistant plastic skinned cable. And so what we're seeing is this moisture resistant has this W in it. And then this doesn't have a W, and this one says it's moisture resistant and it has a W. That W is a sign of a wet rated cable. Now you could have other wet rated cables that are more kind of industry specific, that these are more just kind of general acronyms that you go to Home Depot and you see either THHN cable, which is just a single conductor, high temperature cable that's not for a wet environment. It's a common single conductor cable that's put into homes. Some of these have specific meanings. MI being mineral insulated, underground feeder, UF, underground service entrance. So we have service entrance conductors. We also have this -2 here. This -2 indicates sunlight resistance outside of conduit rating. And so before there was a solar industry specific cable, we were using a lot of say USC2 cable in solar because it was thick enough that we could find it with a thick cable gauge. A lot of this THHN and THWN is done at smaller cable gauges or utility scale cable gauges. And this has a wet rating, sunlight resistance rating. Cables have different cable jacket thicknesses, which can impact how many fit into a conduit. A lot of the conduit calculators are based around THWN and THWN2 cable. Technically the amount of cables that you can fit in a conduit has to do with the area, not the actual cable. So, you can calculate conduit fill percentages without using an online calculator by finding the areas of the cables based off their exact cable jacket dimension, and that's listed in code. What this extra thickness does is it's like the skin of a water balloon. The thicker a plastic is on a water balloon, the more likely you can drop it on the grass without it bursting apart. But the moment that blade of grass hits that water balloon in the right way, cuts through it, boom, there's a explosion. Voltage is kind of the same way. It's how much pressure, that electricity inside the cable can exert on the cable. It's how much water you can squeeze into that water balloon before it explodes, rather than like heats up or deteriorates or melts. So it follows that wet rated cable is a little bit thicker than dry rated cable. If you have an indoor cable, it might have a thinner cable jacket. You replace it with an outdoor cable, then that outdoor cable might not be able to fit so well into the conduit. And furthermore, it's that thicker cable jacket inside that conduit is going to retain heat in the cable a little bit better. So by and large, you want to use indoor cable inside and you want to use outdoor cable outside. Maybe for for a very short run, sure. Now you do get cross-listed cable, so I'm often using THWN2. That's an inside a conduit cable, and just going from the inverter outside the house through the house and then up to the rooftop. Okay, so we started yesterday talking about damp and wet locations. There's actual requirements on metal versus non-metal on whether or not you can just drill the backside of a box directly into the wall. So a lot of professional listed metal equipment will have drill holes that are offset from the back of the box slightly to create that air gap. But if you just bought a generic metal box and screwed it directly to a concrete asphalt wall, that could be a code violation. The temperature differential between the wall and the hotter inside of the box could cause moisture to accumulate, which you don't want around, electrical terminals. But it says, well, if it's plastic, that's fine. Plastic, better insulation, you don't have that issue. Let's see, there's spacing requirements within the box itself to make sure that your live parts are not close to the lid. If you're looking at your electrical box and it's made of metal, and then you're looking at those terminals that are energized hovering a couple of inches off the box, like, well, if I touch those terminals to that metal, what'll happen? You'll cause a ground fault. So you can't get these, if you're building your own box, you can't get too close to the edge or the lid. So here we have one that's a switch overcurrent device enclosures. Splices, taps, and feed through conductors are permitted when the conductors do not exceed 40% of the cross-sectional area of the box. When the total assembly does not exceed 75% of the area. So what does this mean? Well, sometimes you have to splice into a box. Here's a component called a tap connector, and essentially, this is when you're doing that supply side tap. You're bringing, the power comes in from the power company and then goes out towards the comes in from the power company. And you use a bolt to tighten down that lug, and then there's a metal interconnecting bar inside this thing. So you have the power company conductor, the grid, and then you bring in your solar array or your battery inverter in blue, and then you have your electrical load coming out the other side. So this is a tap connector because it taps these three cables into one. We saw earlier that is if they're within 10 feet of the service, then there doesn't need to be overcurrent protection in that line. Anyway, these knuckles take up space. They're larger than the cabling itself, and so what we see in National Electric Code is rules governing both the how large the box needs to be in order for you to not just pass the conductors through the box, but also to do work on them. And then also, the cross-sectional area of the entire box. And we're going to see these requirements reappear in National Electric Code when it turns out to be like, well, what can you put in a box and what can you not put in a box? With smart homes, you want to put energy monitoring equipment inside an electrical box sometimes, and or a electrical service panel. Hey, can I put this device inside my service panel? There may be some more specific rules, but the general rule is, as long as you're not exceeding 75% of the cross-sectional area of that box, one dimension or another, then you're going to be fine. But then on top of that, you want to make sure that you're keeping live parts, away from the door. So that brings us to, can you do if you're allowed to have splices inside of raceways or inside of boxes or inside of conduit, there's some exceptions to say, well, you might think you can put a splice connector here, but you actually can't. So we're getting into smaller conduit bodies. This is called an LB, and you have conduit coming in one way and conduit coming the other, and you use an LB for two reasons. The first reason is you're doing a cable pull and you need to go off the other direction. Generally speaking, with cable pulls, you can, well, not just generally, literally speaking, you cannot pull more than 4 bends. So if you have a 90-degree bend, a 90-degree bend, 90 degrees, 90, that makes 360. And once your conduit forms that circle, then you can't stick your fish tape through it and pull out the cable from one end to the other. It becomes too hard. So you'd put in an access point to better accomplish that cable pull. Well, the other aspect of when you use LBs is when the customer says, I like the way these LBs look better than a 90-degree bend. You could have a 90-degree bend, but if this were done with a 90-degree bend, it would start bending over here and take up a lot more required space to do a EMT tube with a 90-degree bend, whereas with an LB, you get a nice sharp edge. And my experience has been clients don't like it when you have big loopy cables coming, over the edge of a building, that they would prefer something that hugged the profile of the building with a nice sharp edge. I'm going to talk more about that in a minute. But what this rule is saying is, hey, if you have an LB, a small conduit body, just for really pulling cables through and getting you, an access point for your cable pull, that's too small. LBs that enclose conductors number 6 or smaller shall not contain splices, taps, or devices. So we do have a caveat that says, hey, if this LB gets large enough, if you're doing big utility scale work and you have one cable coming in and another cable coming in, you want to put a tap there, you may be able to do that inside larger conduit bodies. Small conduit bodies should not contain splices or taps. Okay, so there's a difference between a cable and a conduit. And there's a difference between a conductor and a cable. And so here we're seeing, this is a conductor table where all of these are single cable conductors. So, this cable has multiple conductors bundled inside of it. Romex, for those AC circuits all throughout your house, has multiple circuits bundled inside of it. And so code has a section for single conductor cables. They also define multiple conductor cables. And then, the way it works is your multiple conductor cables, you're not pulling through anything. They already are kind of done for you. Whereas otherwise, if you're using single conductors and conduit, you build your conduit run and you pull your single conductors through it. So the question is, well, when do you use a pre-made cable and when do you not use it? And, in general construction, using a pre-made cable, if you can get away with it, it might cost a little bit more in material, but you make it up with labor. Now, the problem with solar cable specifically is DC solar cable inside of a building needs to be in metal. And so Romex does not work with solar for running cables through the inside of the building. And that really led to, installers needing, smaller than utility scale cable for home projects, for residential, small solar projects, but not having any product availability. And so the solution was, well, we'll run our metal conduit and pull single conductor cable through it. There is an option, though, for a bundled cable. It costs 3 times as much as in material as buying the conduit and putting the cable inside of it. But by the time you add in everything up, I find it worthwhile. I never regret having it on a job site when we can use it. The pros of metal clad cable, this is not flexible metal tubing where you buy the metal conduit empty and then you pull the cables through it. This comes with, they actually wrap this binding around the cable, and that actually has a difference. If you put this in a larger tube, so that you have to have the empty space so that you can actually pull this cable through, and these ridges make it, and the flexibility of the cable both make it very difficult to pull cable through this stuff. And so you get a hollow flexible metal conduit for short sections where you're pulling single conductor cables through. But because this is more tightly wound around the cables themselves, you get more flexibility in this. And so what this is you can get it in a 1,000-foot spool if you want. So generally I am measuring the runs between the rooftop through the attic and down to wherever the inverter is, and I'm buying enough metal cable to make that run, and I'm just pulling it through the attic and strapping it up to the top of the attic. Not within an inch of the roof, but up at the top in a nice orderly way, and that avoids having to build a conduit run. So when can you use metal clad cable? Some jurisdictions don't let you use this. And I'd say so if you're in a major city that is, I'd say, on the east or the west coast, multi-unit building, they might have a requirement to say, no, we want you to use conduit that's a little bit stronger than this metal clad cable. But I think for solar, this, having this metal is, hey, none of the other power lines in your house are in metal, and the utility feeder entrance conductors inside your house don't even need to be in metal, and they're at a much higher power capacity. I think that this metal protection is really for critters, so that they don't chew up your power lines, and I think that can make sense. That this is one area where the United States has a more expensive solar industry than in other countries, but you get what you pay for. Landing the connectors on this MC cable, if you over tighten them, they can bite into the cable and cause a ground fault. And also metal clad cable, the attic that it's in has to be accessible. You have to be able to kind of see it and walk around it and be able to get up to it. And finally, the last thing with MC cable is it can only be in a damp environment rather than a wet environment. And so generally with this MC cable, here's the house. And if you're putting your inverter on the north side of the building and the solar array is on the south side of the building, here's your solar array up on the rooftop. What I put a specialized metal box right up here on the rooftop, and then I run MC cable through the box, strap it through the attic, and then out the other side. At this point, you have to end your MC cable right underneath the soffit so that it's still protected by the weather. If you run your MC cable all the way down to the inverter, the inspector might say, well, that's not rated for that. So what you can do is buy the length of MC cable to go down to the inverter and then just peel off the metal wrapping and then transition that into EMT conduit. So when I'm buying my MC cable, one of the things that I'm checking is, hey, even though the MC cable has a damp rating, I want to make sure that the cables inside of it are THWN, are wet rated cables, so that I can put it into EMT conduit at that point for the rest of my run down to the inverter. But that actually, it simplifies the installation, because instead of taking your conduit and like snaking it over the side of the roof and around the roof and then around the roof again and then down to the inverter, you can just drill a hole in the roof, throw your MC cable over the other side, and land on your inverter. It's much faster, and I feel much better knowing that the cables of the solar array are protected by the home structure rather than exposed to the great outdoors.